Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below. So, imagine this. If a factory worker accidentally drops a 50-pound sack of flour and it, bursts into the air right next to a conveyor belt motor that has a worn-out overheating bearing, they haven't just made a mess. They've essentially primed a thermobaric bomb that could blow the roof off the facility.
Yeah, it is a truly terrifying reality of industrial manufacturing. I mean, what seems like a completely mundane culinary ingredient just instantly becomes this highly volatile fuel source under the right physical conditions.
And that completely shatters the illusion most of us have about machine design. Usually when we look at a finished product like a sleek new car or an automated CNC mill or even just a heavy-duty coffee grinder, we default to this comforting narrative of singular genius.
Right. The lone inventor.
Yeah. Exactly. One brilliant inventor sitting at a drafting table, sketching out the entire masterpiece. But the reality of building a machine, especially one that processes materials at an industrial scale, is this incredibly intense, highly regulated collision of different engineering disciplines.
Oh, absolutely. You are looking at a multidisciplinary symphony. Building a machine is, well, it's not just about making a set of kinematics work.
Getting a blade to spin is the easy part.
Right. Getting a blade to spin or a press to cycle is easy. The true engineering challenge is making those components move safely, hygienically, and reliably over, millions of cycles, and in environments that range from freezing cold to incredibly hot, all while anticipating every possible way a human operator might interact with it.
Or misuse it.
Or completely misuse it, exactly.
Which is exactly what we are walking through today in this deep dive. We have this massive stack of international and European engineering standards right in front of us. And these are the underlying codes, like the literal rule books governing the physical world.
They really are.
And we are going to use these standards as our ultimate blueprint to take you on a complete, ground-up journey of building a machine from scratch. But we aren't just looking at the metal and the gears. We're going to map out the entire life cycle of the machine and pinpoint exactly when the mechanical, electrical, process, or human factors engineers have to step up and take ownership of a specific standard.
And by the time we've finished mapping this out, your perception of the everyday machinery around you is going to completely change. You're going to start to see the hidden logic.
Yeah.
Every seemingly random piece of bent steel, every warning icon on a digital interface, every specific gap between two moving parts, it all exists for a heavily debated, scientifically documented reason.
So let's start at absolute zero. We have a blank whiteboard.
Yeah.
We have a conceptual idea for a brand new, large-scale industrial food processor. Before anyone opens a CAD program to draw a gear or, calculate a torque requirement, where does the actual engineering begin?
Well, based on the general principles of machinery safety, the very first step is entirely theoretical. We have to map out the intent and the failure modes, which puts us squarely in the domain of the systems engineer and the safety engineer. Everything starts with the risk assessment.
So no drawing yet, just planning.
Just planning. The engineers must rigorously define the intended use and, just as importantly, the foreseeable misuse of the machine. And when you are dealing with food processing equipment, the standards mandate that the nature of the food fundamentally dictates the entire mechanical and control architecture from day one.
I really want to dig into that phrase, the nature of the food, because, to a layperson, food is just food. A carrot is a carrot.
Right.
But I'm guessing an engineer looks at a raw, dirt-covered carrot very differently than they look at, say, a jar of pureed carrot baby food.
They absolutely have to. The risk profile shifts radically depending on the state of the material. Is the machine processing raw, unwashed materials arriving straight from the agricultural field?
Okay.
Or is it handling part-processed ingredients? Or is the output ready for direct human consumption without any further cooking or sterilization?
So if it's the raw stuff, the rules are different.
Very different. If you are building a machine that processes raw potatoes, you are dealing with abrasive dirt, stones, and field bacteria. The machine needs to be robust, but the immediate biological risk to the consumer is relatively low because, well, the potato will be washed and cooked later.
But if you are building the machine that fills the final jar of baby food, the acceptable threshold for biological contamination drops to absolute zero.
Zero, yes. The standards explicitly force the systems engineer to consider the end consumer. Are we feeding healthy adults with robust immune systems, or are we feeding a vulnerable population?
Like infants or the elderly.
Exactly. Infants, the elderly, immunocompromised hospital patients. If the target demographic is vulnerable, the risk assessment mandates entirely different tiers of control measures.
Oh, wow.
Yeah, the materials you use, the cleaning cycles, the sealing mechanisms, they all have to be upgraded to essentially pharmaceutical grade levels of hygiene.
So the systems engineer and the safety engineer are sitting in this room running through what I imagine is a failure mode and effects analysis, an FMEA.
Yes,
They
exactly.
are looking at every single pinch point, every spinning shaft, every potential source of bacterial growth, and every way an operator could get hurt. And the core strategy they are required to follow is this hierarchy. It's eliminate, reduce, then safeguard.
That is the holy trinity of safety engineering right there. The first imperative is always elimination. Can we design the hazard out entirely?
Right. It's like building a house.
Yeah.
You don't pick the paint colors before you pour the foundation.
Perfect analogy. If there is a risk of a crushing injury from a pneumatic press, the first question is, can we change the mechanism so it doesn't need a press at all?
And if you can't,
If you can't eliminate the hazard, you move to reduction. Can we lower the speed? Can we reduce the pneumatic pressure so that even if it hits a hand, it doesn't break a bone?
but what if we can't reduce it? Because the machine physically needs that high pressure to punch through the material.
That's when we finally move to the third step, safeguarding. We put a physical wall around it.
Okay, but I have to push back here. Isn't risk assessment just formalized common sense? I mean, obviously, you don't put a razor-sharp spinning blade where an operator stands. Why do we need a massive, hundreds of pages standard for it?
It's a fair question, and junior engineers often think the exact same thing. But common sense is highly subjective, and it fails miserably when dealing with complex, cascading system failures.
Cascading failures, like what?
Well, common sense tells you not to touch the blade when it's spinning. But common sense doesn't tell you what happens if a microchip overheats, which causes a sensor to falsely read that the access door is closed, which then allows the main motor to fire up unexpectedly while a maintenance worker is inside the machine cleaning that blade.
Oh, man. Yeah, I see what you mean. Common sense doesn't cover a random microchip melting.
Exactly. That is the exact scenario these standards are built to prevent. Formalizing the risk assessment forces the engineering team to acknowledge what we call residual risks.
Meaning, the danger that is left over after you have designed out, reduced, and safeguarded everything you possibly can.
Right. No machine that performs useful mechanical work is 100% safe. If a blade is sharp enough to cut a carrot, it is sharp enough to cut a finger. The safety engineer's job is to mathematically document every single residual risk so the design team can build specific mitigations against them.
Okay, so the safety engineer has mapped out this matrix of doom. They have identified the crushing zones, the shearing hazards, the entanglement risks. Now, they hand those theoretical blueprints over to the mechanical engineer.
Because the abstract risk has to be translated into physical geometry.
Right. The mechanical engineer's job is to build a fortress around those hazards using fixed and movable guards and calculating safety distances.
This is where we dive into heavy anthropometric data. The mechanical engineer isn't just like eyeballing how big a human arm is.
They're not just guessing.
No, not at all. They are using highly specific, standardized data sets of human proportions to determine exactly where a guard needs to be placed.
Okay, so looking at the sources, the benchmarks in the standards rely on the 5th percentile stature of a 14-year-old, which is approximately 1,400 millimeters. Why a 14-year-old? I'm assuming if you design a safety guard for the average person like the 50th percentile, you are basically leaving the smaller half of the population completely vulnerable.
That is the exact rationale. By basing the safety mathematics on a person who is 1,400 millimeters tall, with correspondingly smaller arms and thinner fingers, you create a worst-case scenario for penetration.
Because smaller fingers can slip through smaller gaps.
Exactly. If a small, slender finger cannot slip through the mesh of a safety guard to reach a spinning gear, then a larger, thicker adult finger certainly cannot.
And for reaching through openings, the standards get even more restrictive, right?
They really do. If the machine has an opening where upper limbs could reach through like a material feed chute or a ventilation grate, the standards require protection based on children 3 years and older.
Well, 3 years old.
Yes, which correlates to a stature of approximately 900 millimeters.
Though the text does specify that protection against strangulation isn't covered here, just reaching through with limbs.
Right. The focus in this specific standard is strictly on preventing access to the hazard zone. The mechanical engineer has to calculate the relationship between the size of the opening and the distance to the dangerous mechanism. It is a strict geometric ratio.
Let's walk through the math on those openings. The sources state that if you have a slot opening and the length is less than or equal to 75 millimeters, the safety distance can be reduced to 50 millimeters.
Correct.
So if I have a 75 millimeter slot, I only need to put the spinning blade 50 millimeters behind it. Why is that allowed? That seems really close.
Think about the physical mechanics of the human hand. If a slot is 75 millimeters or smaller, you can get your fingertips and maybe the flat of your fingers through it.
Okay.
But the width of your knuckles or the thicker heel of your palm will physically block your hand from penetrating any further. Your hand essentially wedges in the slot.
So you just get stuck.
Exactly. Because the geometry of the opening physically arrests the forward momentum of the arm, the engineer knows your fingertips can only reach a maximum of, say, 40 or 45 millimeters into the machine. Therefore, placing the hazard 50 millimeters back is mathematically safe.
But if that opening is greater than 100 millimeters, the rules change drastically.
They have to. An opening of 100 millimeters or more allows a smaller adult or a teenager to slide their entire hand through. And once the hand clears the opening, the wrist and elbow can follow.
And suddenly they're arm deep in the machine.
Right. Suddenly that operator can reach half a meter into the machine. So if the opening is that large, the safety distance from the guard to the blade might have to be extended to 850 millimeters or more, just to ensure their fingertips can't graze the danger.
So every single vent hole, every observation window, and feed slot has to be calculated against these tables.
Every single one.
Now, what about just building a solid wall around the machine? Because the standard mentions that protective structures less than 1,000 millimeters in height are entirely excluded from the safety tables.
Yeah, because a wall that is less than a meter high isn't a barrier. It is a trip hazard.
Oh, that makes sense.
Right. A person can simply step over it, they can lean heavily over it, or they can fall across it. It doesn't meaningfully restrict the movement of a human body towards a hazard point.
Okay, so let's say the mechanical engineer builds a solid steel wall exactly 1,400 millimeters high. That matches that 5th percentile stature benchmark we talked about. Can they just put the hazard right behind that wall and call it a day?
No, because they have to account for the pivot points of the human body. The shoulder, the elbow, the wrist. We aren't just trying to stop someone from walking directly into the machine. We have to stop them from reaching over the protective structure.
So if I have a crushing mechanism located high up on the machine, let's say at a height of 2,400 millimeters, and my guard wall is 1,400 millimeters high.
Well, if a person walks up to that 1,400 millimeter wall, they can easily reach their arms up and lean their torso forward over the top edge. The standard provides specific trigonometric tables for this exact posture.
Math for leaning. I love it.
It is, and according to those tables, if the hazard is at 2,400 millimeters and the wall is at 1,400 millimeters, the mechanical engineer must enforce a horizontal safety distance of 1,100 millimeters between the top of the wall and the hazard.
Meaning the danger has to be pushed over a meter away from the wall, deep inside the machine's footprint, so that even if I am leaning over the barrier and stretching my arm as far as I possibly can, I am literally grabbing empty air.
Exactly. The mechanical engineer is not just designing a flat wall, they are designing a three-dimensional safety envelope. They are predicting how a human skeleton bends and stretches, and they are putting physical steel in the way to disrupt that reach.
That is fascinating.
And they also have to account for foreseeable misuse. What if the operator uses a broom handle to try and poke at a jammed piece of material?
Right, because if an operator is frustrated because a feed chute keeps jamming, they're going to grab whatever tool is nearby to clear it without walking all the way around to the main access panel. The engineer has to anticipate human impatience.
Which is exactly why the guards often feature tortuous paths.
Like a maze.
Like a maze-like chute with internal baffles, yes.
Yeah.
So you physically cannot push a straight rod down into the moving parts.
Okay, so the mechanical engineer has built an absolute fortress. The slot widths are mathematically proven to stop fingers. The guard heights and horizontal distances account for leaning and stretching. The physical geometry is perfectly sound. But a steel wall is completely blind.
It is.
A heavy seal door doesn't know if it's open or closed. If an operator opens the guard door to clean the machine and the motor keeps running, The physical guard hasn't accomplished anything.
Right. The machine needs to be self-aware. It needs to monitor its own physical boundaries.
Which brings in the electrical engineers and the software controls engineers to give the machine a nervous system. And the standards refer to this as the safety-related parts of control systems, or SRPCS.
That's right.
So we're talking about the sensors that detect the door opening, the logic units that process that sensor data, and the power elements like the massive electrical contactors that actually cut the voltage to the motor.
The very first thing the electrical engineering team has to define is the strict separation between an operational function and a safety function.
Okay, I try to picture this like the human central nervous system.
How so?
Well, an operational function is like walking, right, or reaching for a glass of water. It is intentional, conscious control. You press the green start button on the HMI screen, the programmable logic controller, the PLC, tells the drive to spin up the motor, and the conveyor belt moves.
Right.
But a safety function is entirely different. It is the human reflex when you accidentally touch a hot stove. Your spinal cord yanks your hand back milliseconds before your brain even registers the sensation of heat. It has to bypass conscious thought. It has to be instantaneous and absolute.
That analogy perfectly captures the architectural philosophy. A machine's safety function must be fundamentally more reliable and faster than its operational functions. And the standards classify this required reliability into performance levels and categories.
The standard contrasts Category B with Category 4. If I'm looking at a machine's electrical schematic, what is the fundamental difference in how those two systems are built?
Category B is the absolute baseline. It stands for basic safety principles. A Category B control system is designed using standard, reliable components that can withstand expected environmental influences.
Like normal vibrations, heat, electrical noise.
Exactly. But the architecture is single channel. There is one sensor, one wire, one processor, and one relay.
So any one of those things fails, say, the wire from the door switch snaps from metal fatigue, the system is entirely blind.
Yes. The safety function is just lost. The operator could open the door and the machine would not stop because the signal never reaches the controller. So Category B is only acceptable for extremely low-risk applications where an accident might cause, a minor bruise.
But for an industrial food processor with massive shearing blades, a snapped wire cannot result in an amputation.
We have to jump to the other end of the spectrum, which is Category 4. Category 4 is the gold standard for high-risk machinery. The defining architectural rule of Category 4 is that a single fault in any part of the system must not lead to a loss of the safety function.
Not even one fault.
Not even one. And furthermore, that fault must be detected by the system at or before the next demand on the safety function.
Okay, I understand how you achieve that with physical wiring. You run two completely separate wires from the door sensor. If one wire snaps, the second wire still carries the signal to stop the machine. The computer sees that wire A has 0 volts and wire B has 24 volts, realizes there is a discrepancy, and throws a fault code.
That's the hardware side, yes.
But modern safety systems aren't just copper wires and mechanical relays anymore. They are driven by microprocessors and millions of lines of software code. You can't measure a software bug with a voltmeter. How do you build a Category 4 system out of software?
This is the deepest, most complex challenge for a controls engineer. You cannot predict a logic error in software the same way you can predict the mechanical wear of a relay contact. So, the standards use concepts like fault exclusions and require highly specific redundant architectures. You don't just use one microprocessor to run the safety code. You use a dedicated safety PLC.
And a safety PLC is physically different from a standard industrial computer.
Radically different. A safety PLC utilizes dual-channel hardware redundancy and software diversity. Inside that yellow casing, there are often two completely separate microprocessors. In the most rigorous designs, those chips are sourced from entirely different manufacturers.
Wait, really? Why different manufacturers?
Because if there's a fundamental microscopic flaw in the silicon design of one chip, you don't want the exact same flaw mirrored in your backup chip.
Oh, that makes total sense.
Right. Furthermore, the code running on those two chips might be written by two different programming teams, or one processor might use inverted logic compared to the other. Both processors independently monitor the safety door. If the door opens, both processors run their distinct logic paths and must independently arrive at the exact same conclusion. stop the machine.
They're essentially voting on the safety of the machine every few milliseconds.
Exactly. And they're constantly performing diagnostic monitoring on each other. They exchange clock cycle pulses thousands of times a second. If processor A says keep running, but processor B says stop, the discrepancy triggers an immediate system halt. Even if processor A simply takes 3 milliseconds too long to respond to the heartbeat check, the system defaults to a safe state and cuts the power.
That is wild. This brings up the parameters of reliability mentioned in the sources: mean time to dangerous failure, diagnostic coverage, and common cause failure.
Right. Let's break this down. Mean time to dangerous failure is a statistical probability calculation. Based on laboratory testing of components, how long, on average, will it take for a specific relay or sensor to fail in a way that actually masks a danger?
Okay, and diagnostic coverage.
Diagnostic coverage measures the system's self-awareness. What percentage of potential dangerous failures can the dual-channel architecture actually detect and flag before an accident happens?
And then there is common cause failure. I'm guessing a common cause failure is an external event that wipes out both of your redundant channels at the exact same time.
Yes, exactly.
Like putting both of your safety microprocessors in the same unventilated plastic box, the cooling fan fails, and both chips overheat and melt simultaneously. Your redundant voting system is completely useless.
You hit the nail on the head. Or consider electromagnetic interference. If a massive main drive motor starts up and sends a huge spike of electromagnetic noise through the factory, it could scramble the signals on both safety channels simultaneously if the cables are routed next to each other.
So how do you engineer against that?
Engineering against common cause failure means physically separating the wire routing, adding optical isolators to protect against power surges, and ensuring that no single real-world event can compromise both sides of the safety nervous system.
The level of paranoia required to be a good controls engineer is just staggering.
Yeah.
So let's take stock of the machine we are building. The safety engineer defined the hazards. The mechanical engineer built a physical fortress of calculated steel. The electrical and software engineers gave the machine an incredibly resilient, self-diagnosing Category 4 nervous system. From a mechanical and electrical standpoint, the machine is perfectly safe for the human operator.
But we established at the beginning that this is an industrial food processor.
Right.
Protecting the operator from the machine is only half the battle. We also have to protect the product from the machine. A food mixer can be mechanically perfect and electrically brilliant, but if it is harboring microscopic pathogens in a hidden crevice, it will poison thousands of people. It is a catastrophic failure.
Which means we are bringing in the process engineers, the chemical engineers, and the food scientists.
Exactly.
The primary objective, dictated by the hygiene standards, is to eliminate hygiene risks to the food and reduce contamination risks to an acceptable level through cleanability. The very first mandate is to strictly define the geography of the machine into food areas and non-food areas.
And that distinction requires a deep understanding of operator workflows. A food area is obviously the inside of the mixing bowl or the surface of the cutting blade. But the standards state that even a control device like a push button on an HMI screen or an emergency stop switch becomes a food area if the operator touches it with food-covered hands, causing cross-contamination.
That makes perfect sense. If an operator is handling raw chicken, reaches over to hit the stop button, and then an hour later handles cooked, ready-to-package chicken, and hits that exact same button to start the line.
The button just acted as a bridge for salmonella.
Right, so the button itself, the physical switch on the outside of the machine, has to be designed to hygienic standards.
Precisely. And achieving hygienic design at the metallurgical level is incredibly demanding. It starts with surface finishes. The standards mandate that surfaces in the food area must be smooth, continuous, and sealed. They specify exact surface roughness values.
Yeah, the text mentions that they must have a finish so that no particle of product becomes trapped in small crevices, becoming difficult to dislodge.
Because if a microscopic particle of protein or fat gets trapped in a tiny scratch in the stainless steel, it becomes a localized food source for bacteria.
Huh?
And over time, that bacteria multiplies and forms a biofilm, which is this tough protective matrix that shields the bacteria from chemical cleaners. Once a biofilm is established, it will constantly shed bacteria, contaminating every single batch of food that passes over that surface for months.
To prevent this, the engineers have to eliminate what the standards call dead spaces. And this leads to one of the most rigidly defined geometric rules in the entire deep dive. The standard explicitly states that for internal corners, if the internal angle is less than 135 degrees, the radius must be greater than or equal to 3.0 millimeters.
Yes. This is one of those specific details that beautifully bridges macroengineering with microbiology.
I want to push back on this just to understand the reasoning.
Go ahead.
If I am running a massive industrial food plant, I am not cleaning these machines with a sponge, right? I am blasting the entire line with scalding hot water, caustic chemicals, and high-pressure steam. Why do we need to obsess over a 3.0 millimeter curve on an inside corner? What, high-pressure bleach just kill everything anyway?
You would think so, but the fluid dynamics say otherwise. Industrial food machines are massive. You cannot tear down a 50-foot processing line every night with wrenches to scrub it by hand. They rely on CIP cleaning in place and CSIP sterilization in place. You hook up massive pumps and circulate cleaning fluids through the assembled machine.
Right, you are relying on the velocity of the fluid to do the scrubbing for you.
Exactly. And fluids in motion follow the path of least resistance. We are talking about boundary layers and shear stress. If you machine a piece of steel with a sharp 90-degree internal corner and you pump fluid past it, the fluid is not packed perfectly into that sharp point.
What does it do?
The flow separates. It creates a microscopic eddy, a stagnation zone or shadow area, right in the apex of the corner where the fluid velocity drops to nearly zero.
Oh, wow. So the high-pressure chemicals just rush right past the corner, leaving the microscopic debris untouched.
The chemical cleaners never reach the apex with enough kinetic energy or shear force to physically strip the biofilm off the steel. The bacteria simply hunker down in that microscopic low-pressure shadow, survive the hour-long CIP cycle, and then bloom again the moment the machine starts processing warm food.
Yeah, it is terrifying.
It is. By legally mandating a smooth, sweeping radius of at least 3.0 millimeters, the standard forces the engineer to shape the steel so that the fluid maintains laminar flow, sweeping smoothly through the curve and scouring the surface completely clean.
You are literally manipulating fluid dynamics with a piece of bent steel to prevent a microscopic bacterial colony from finding a safe harbor. That is brilliant.
And the scrutiny only intensifies when you look at moving parts. Take a shaft seal. If you have a massive mixing paddle inside a vat, the drive shaft has to pass through the steel wall of the vat to connect to the motor outside. That penetration point, the seal, is the ultimate contamination risk.
And the standards dictate that these shaft seals must be self-lubricated or use highly specific food-grade lubricants.
Correct.
And the sources mention that in extreme applications, a double seal with a continuous sterile barrier is required. How does a continuous sterile barrier actually work mechanically?
Well, imagine that spinning drive shaft passing through the wall. Instead of one rubber gasket, you design a housing with two separate mechanical seals spaced a few inches apart along the shaft.
Okay.
Into that gap between the two seals, the machine constantly injects high-pressure, superheated steam or a liquid antimicrobial solution.
So the space between the inside of the food vat and the outside industrial environment is pressurized with steam.
Yes. Because it is pressurized, the pressure differential dictates that if the inner seal fails, the food inside the vat cannot leak out into the gears, and the industrial grease from the motor cannot leak into the food. The high-pressure steam acts as an impenetrable, continuous wall of sterile energy, blocking any physical or biological transfer.
Okay, our process and chemical engineers have done their job. The machine is microbiologically immaculate. Fluid dynamics guarantee it can be cleaned, and steam barriers isolate the food from the mechanics. The bacteria have been defeated.
For now, yes.
But while bacteria are a silent microscopic threat, our next engineering challenge is loud, violent, and macroscopic. This brings us to the ATEX directives, which govern equipment intended for use in potentially explosive atmospheres.
This is where we circle back to the scenario we discussed at the very beginning of the deep dive, the dust explosion.
If I am designing an oil refinery or a chemical plant handling volatile solvents, I absolutely expect to be dealing with explosion prevention. But we are talking about a food mixer. We are handling sugar, wheat flour, powdered milk, maybe some cornstarch. Why are specialized safety engineers being brought in to prevent explosions in a bakery?
Because of the physics of combustible dust. It is highly counterintuitive, but the reality is that the dust explosion pentagon governs these environments.
The dust explosion pentagon.
Yes, you need 5 elements: fuel, oxygen, heat, dispersion, and confinement.
Let's break those down. The fuel is the food.
Yes. If you have a solid block of sugar and you hold a blowtorch to it, it will caramelize and burn slowly. The surface area exposed to oxygen is very low.
Right, it just kind of melts.
But if you pulverize that sugar into a fine dust and then disperse it into the air, creating a suspended cloud inside a machine hopper, you have drastically increased the surface area. Every single microscopic particle of sugar is now completely surrounded by oxygen.
That covers fuel, oxygen dispersion and confinement inside the hopper. All you need is the fifth element, heat, or an ignition source.
And it doesn't take a blowtorch. It takes an incredibly small amount of energy, what we call the minimum ignition energy, or MIE. If a single spark is introduced into that suspended cloud, one dust particle ignites.
Run.
The heat from that tiny combustion instantly ignites the dust particles millimeters away, which ignite the ones next to them. The chain reaction propagates outward at supersonic speeds. Because this is happening inside the confined steel walls of the mixer, the expanding gases create a massive pressure wave that can rupture the machine and trigger secondary explosions throughout the factory.
So what generates the spark inside a stainless steel machine? I mean, where does it come from?
Mechanical friction is a massive culprit. A bearing wears out, loses its lubrication, and starts grinding. The metal-on-metal friction generates intense heat. If the surface temperature of that bearing housing reaches the auto-ignition temperature of the specific flour dust settling on it, it will trigger an explosion. Static electricity is another huge factor.
Static, like rubbing a balloon.
Exactly. Powders sliding down plastic chutes or moving on ungrounded conveyor belts can build up massive static charges, which eventually arc across a gap, creating a spark.
The ATEX directives place the ultimate responsibility for conformity on the manufacturer. They must understand the thermal and mechanical stresses their machine will undergo. How do they engineer around this?
They utilize intrinsically safe circuits and dedicated safety devices. They install vibration monitors to detect a failing bearing before it gets hot. They use thermal sensors on the bearing housings. They use specialized grounding straps to dissipate static.
But the sources highlight a critical architectural rule for these ATEX safety devices. A safety device preventing an explosion must function completely independently of any measurement or control devices required for normal operation.
This is a vital point of isolation. Imagine you have a temperature sensor inside the mixer. During normal operation, the main PLC uses data from that sensor to decide when to turn on a cooling jacket to keep the dough from getting too warm and ruining the yeast.
Okay, so the PLC is using that sensor for operational control.
Right. But if you want to protect against a fire or explosion, you cannot use that same temperature sensor to trigger the emergency shutdown. You must install a completely independent, redundant thermal sensor that is wired to a separate safety relay.
Why? To avoid that common cause failure we talked about.
Exactly, because if the single shared sensor fails, or if the main PLC crashes, you lose both your ability to bake the bread properly and your ability to prevent the machine from exploding. You have a common cause failure.
Wow. You must isolate the safety systems from the operational systems.
Yes, the ATEX engineering requires a paranoid separation of duties to ensure that an explosion prevention system is never compromised by a routine operational failure.
The layers of engineering interacting here are just staggering. Okay, let's step back and look at our creation. The safety engineer identified the risks. The mechanical engineer used anthropometric geometry to build a physical fortress so arms can't reach the blades. The controls engineer built a dual-channel Category 4 microprocessor nervous system to monitor the doors. The process engineer manipulated fluid dynamics with 3.0 millimeter radii to eliminate bacterial shadow areas. And the ATEX chemical engineer isolated the electronics and monitored friction to ensure a suspended cloud of flour dust doesn't ignite.
It's a lot of engineering.
It is. The machine is mechanically safe, electronically self-aware, microbiologically hygienic, and thermally stable. It seems perfect.
It is a technical masterpiece, but it still has one chaotic, unpredictable variable interacting with it every single day.
The human operator.
The human operator. And that brings us to the realm of the human factors engineers, the UI/UX designers, and the technical communicators.
As we established in the very first step of the risk assessment, we cannot eliminate all risks by design. There is always residual risk. If a heating element needs to be at 400 degrees to seal a plastic bag of food, we cannot eliminate the heat, and if the operator needs to manually feed the plastic into the sealer, we can't completely enclose it. The residual risk is a severe burn.
Exactly.
The ISO 3864 standard dictates that this residual risk must be communicated through product safety labels and screen icons.
Right. This is where engineering intersects with cognitive psychology. The standards govern exactly how we communicate danger to break through human complacency.
And it starts with the signal words. We see these words on products every day, but the standards draw a rigid, legally defined line between words like danger and caution.
Mostly, people use those words interchangeably. I mean, danger, caution, warning, it's all the same to us. But the standards do not. The word danger is reserved exclusively for the most extreme situations. It indicates an imminently hazardous situation that will result in death or serious injury if not avoided. The operative word is will. It is absolute certainty of catastrophic harm, high voltage, exposed crushing gears, lethal chemical exposure.
Whereas caution indicates a potentially hazardous situation that could result in minor or moderate injury, like a surface that might be hot enough to cause a mild blister, but won't melt your hand off.
Exactly. You scale the language to the severity of the hazard, and the physical layout of these warning labels is strictly governed. You have the hazard severity panel at the top, featuring the signal word and a universally recognized graphical symbol like the exclamation mark in a triangle or the jagged lightning bolt.
And then below that,
Below that, you have supplementary safety text panels that briefly explain the nature of the hazard and exactly how to avoid it.
but machine interfaces aren't just stickers on steel anymore. Modern machinery is driven by complex digital screens, HMIs, and touchscreen panels. The ISO 80416 standard covers the adaptation of these graphical symbols for digital screens. This is where it gets surprisingly technical for a graphics discussion. The standard forces the engineers to utilize rendering techniques like anti-aliasing.
This is a fascinating intersection of software graphics and safety. Anti-aliasing is a technique used in computer graphics to smooth out the jagged, pixelated edges of a curved line on a digital display.
I understand anti-aliasing in the context of high-end video games to make the graphics look realistic, but how does it technically work, and why does an international safety standard care about it on a factory machine?
Technically, anti-aliasing works by using intermediate intensities of color subpixel rendering or alpha blending between the edge of the line and the background color. It tricks the human eye into perceiving a perfectly smooth curve, even on a screen with a relatively low pixel density.
Okay, I follow that.
And safety standards care deeply about this because of the viewing environment.
Right, a factory floor is not a pristine gaming setup.
Exactly. An operator might be glancing at a control screen from 4 feet away under harsh, flickering fluorescent lights while wearing safety goggles with the screen covered in a layer of flour dust. If an icon representing a spinning hazard, which is essentially a series of curved arrows, is rendered without anti-aliasing, the jagged, stepped pixels can visually blur together.
So what happens then?
From a distance, that curved arrow might look like a solid square box or just a generic blotch of color. The operator misinterprets the icon, misunderstands the state of the machine, and makes a fatal error. The icon must be instantly, universally distinguishable, regardless of the screen resolution.
Okay, I have to play the skeptic here. Let's look at actual human behavior. People buy a brand new extension ladder. It is plastered with brightly colored danger stickers, and they completely ignore them. They buy a kitchen appliance, throw the manual in the trash, and just start pressing buttons.
We all do it.
Right. Isn't all this obsessive work by the human factors engineers just legal cover for the manufacturer? A way for corporate lawyers to say, hey, we put the sticker on the machine, we use the right anti-aliasing, so if you get hurt, you can't sue us.
It is very easy to become cynical about warning labels, especially when we see so many of them, but I have to push back on that assumption. Good human factors engineering is not about legal deflection. It is about cognitive interruption.
Cognitive interruption.
The engineers are fully aware that you are complacent. They know that operators suffer from alarm fatigue and visual habituation.
Meaning they see the machine every day, so their brain just stops registering the warning signs?
Exactly. That is precisely why the standards mandate highly specific chromaticity, coordinates exact shades of safety orange and safety red in universal primal geometric shapes. They are designing these visual cues to bypass the slow language processing centers of the frontal lobe and directly strike the primal pattern recognition centers of the visual cortex. A well-designed, high-contrast hazard symbol jolts the brain out of its habituated state.
And on the digital side?
On digital screens, intuitive UI design reduces the cognitive load on the operator. If a screen is cluttered with poorly rendered icons and confusing menus, the apparent complexity of the machine skyrockets. Under stress, a confused operator is dangerous. But if the interface is clean, anti-aliased, and uses standardized icons, the operator immediately understands what the machine is doing. They maintain situational awareness.
In that sense, good UI/UX design is quite literally a physical safety feature.
It really is.
That reframes it perfectly. You were engineering the human psychological response to the machine, trying to keep their cognitive load low so they don't make a panic decision.
Precisely.
All right, we have marched through all 6 phases of this incredible life cycle, from the abstract risk matrix to the trigonometric physical guards, the dual-channel software logic, the fluid dynamics of hygiene, the physics of explosion prevention, and finally, the cognitive psychology of the user interface.
We've covered a lot of ground.
We really have. Let's put all of these intersecting rules to the test. Let's look at a deep, comparative case study using 2 real-world examples straight from the sources to see how these exact same engineering principles scale up and down depending on the machine.
Let's compare 2 machines that ostensibly perform the exact same core mechanical function. They mix food ingredients using spinning blades.
Okay.
We will look at a consumer countertop food processor, a blender, and a massive industrial dough mixer used in a commercial bread factory.
Let's start with the kitchen blender. The standard divides these into Type 1 and Type 2 machines based on their configuration. But the geometric restrictions on the feed openings are identical. The standards state that the length of the opening must be greater than or equal to 120 millimeters, and the depth or width must be less than or equal to 52 millimeters.
Picture the shape of a standard blender lid. It usually has that small, removable plastic cap right in the center so you can drizzle oil or drop small ingredients in while the blades are running. That opening can be fairly long across the top, up to 120 millimeters, but the depth of the slot is strictly restricted to 52 millimeters.
Why that specific dimension? Why 52?
Because 52 millimeters is mathematically calculated to be too narrow for an adult to easily shove their hand through. If you try to force your hand down that slot to dislodge a piece of frozen fruit near the blades, your knuckles will physically jam against the 52 millimeter restriction long before your fingertips reach the hazard zone at the bottom of the pitcher.
It is designed to allow a carrot to pass through, but physically arrest a human hand.
Pure, elegant, geometric safety.
And the standard also enforces a strict stopping time rule. The blades must come to a complete halt within 4 seconds when the machine is running empty. How do they achieve that mechanically?
It requires managing inertia. An empty blade spinning at 20,000 RPM has a tremendous amount of kinetic energy. If you cut the power, it wants to keep spinning. The electrical engineers might have to implement braking resistors or active motor braking circuits to violently bleed off that kinetic energy and force the spindle to stop within that 4-second window.
Furthermore, the machine must be interlocked so it physically cannot start if the pitcher is incorrectly fitted to the base.
All of those features, the 52 millimeter geometry, the rapid braking, the mechanical interlocks, are safeguards specifically engineered for an untrained consumer operating in an uncontrolled home environment.
Now let's scale up. Let's walk onto the factory floor and look at the industrial mixer. This is a huge open vat. You have operators dumping 50-pound sacks of flour and massive blocks of yeast into a hopper the size of a car. You can't just put a tiny 52 millimeter slot on a factory mixer. The operators need total access.
The scale changes, so the rules change entirely.
Because you can no longer rely on a plastic lid with a small slot to protect the operator, the engineering focus shifts dramatically toward the environment surrounding the machine and active electronic safeguards. The standard starts by looking at the operator's footing. It mandates that elevated work platforms surrounding the mixer must be greater than or equal to 500 millimeters wide.
Because if a worker is wrestling with a heavy sack of flour on a narrow ledge, they might lose their balance and fall forward into the open hopper.
Exactly. You have to ensure a stable, wide footprint. And because the hopper is wide open, the edge protections are radically different. You aren't relying on physical geometry to stop a hand. You're relying on sensors to detect a body. The standards require a mechanical trip bar, a protective grid, or a light barrier array around the upper edge of the hopper.
Let's talk about the light barrier, because that is a sophisticated piece of safety tech.
Yeah, how does that work?
A light barrier, or a safety light curtain, is an array of photoelectric transmitters and receivers. The transmitter sends multiple parallel beams of infrared light across the opening of the hopper to the receiver. If an operator leans too far in and their body breaks even one of those invisible laser beams, the receiver's output signal drops instantly.
This routes right back to the Category 4 safety PLC we talked about. The PLC detects the broken beam and instantly fires the contactors to kill the massive mixing arms.
Exactly. And the physical dimensions of the machine must be calculated to accommodate the reaction time of that electronic system. The standard dictates that the design dimension from the standing area stretching across the upper edge of the hopper and down to the hazard point, the spinning dough hooks, must be greater than 250 millimeters.
Over 2¼ meters. Why so deep?
Because that is the calculated safety envelope required to ensure that even a very tall operator, stretching forward at full speed, cannot physically reach the crushing arms in the fraction of a second it takes for the light curtain to detect them, the PLC to process the signal, and the massive mechanical brakes to arrest the momentum of the steel arms. The distance buys the machine the time it needs to stop.
And when it comes to industrial machines, we also have to consider maintenance. If a technician needs to climb inside that massive hopper to clean it or replace a bearing, a light curtain isn't enough. They need absolute certainty that the machine won't start.
Which is why the engineering must integrate seamlessly with LOTO lockout-tagout procedures. The electrical panels must be designed so that the main energy isolation switch can be physically locked in the off position with a padlock. The technician puts their personal padlock on the switch, puts the key in their pocket, and clangs into the machine.
Because as long as that padlock is on the switch, no other operator can accidentally walk up to the HMI screen and start the machine while the technician is inside. It is a brilliant blend of mechanical design and operational procedure.
It really is.
So, synthesizing all of this, the difference between a My Kitchen smoothie maker and a massive factory dough mixer is not just scale. It's not just the same physics built out of thicker metal.
Not at all. It is a fundamental paradigm shift in the type of human interaction. A consumer blender relies heavily on passive geometric restrictions, small openings, tall pitchers. It physically limits your ability to reach the danger because the engineer must assume you have zero safety training and will do foolish things. An industrial mixer, however, requires active electronic safeguards, light barriers, trip bars, Category 4 voting processors, and lockout-tagout integration.
Because the factory operator needs full, unimpeded physical access to the hopper to do their job efficiently.
Exactly. You cannot put a solid lid with a tiny slot on an industrial mixer while workers are dumping in hundreds of pounds of ingredients. You have to remove the physical barrier and replace it with an invisible, electronic, highly responsive barrier. And that requires vastly higher categories of logic, deeper risk assessment, independent explosion monitoring, and entirely different maintenance protocols. The specific environment, the specific task, and the specific user dictate the engineering approach completely.
That brings this entire journey full circle. We started with the systems engineer staring at a blank whiteboard asking, who is using this, and what exactly is the nature of the food? And we end with the machine physically reacting differently, using either passive geometry or active lasers, depending on the answer to those exact questions.
Yeah, the initial questions drive everything.
Let's recap this massive multidisciplinary process. Building a machine is the ultimate team sport. It begins with the safety engineer systematically predicting the future through risk assessment, identifying every way the system could fail.
Right.
Then the mechanical engineer steps in, armed with human anatomical data, calculating slot widths and guard heights down to the millimeter to build a physical fortress.
Then the electrical and software engineers wire up the nervous system, writing redundant voting code on dual-chip architectures to ensure a single snapped wire or software bug doesn't cost an operator their arm.
And then the process engineers take the design down to the microscopic level, utilizing fluid dynamics to sweep bacteria out of 3.0 millimeter radii and building continuous sterile seam barriers, while chemical engineers isolate the sensors to ensure suspended dust clouds don't ignite into thermobaric explosions.
And finally, the human factors designers step in to bridge the gap between the cold logic of the machine and the chaotic psychology of the human mind, using subpixel anti-aliasing and highly specific chromaticity to break through our natural complacency. Every single millimeter of steel, every line of code, every curved corner, and every colored pixel exists for a scientifically documented, endlessly debated reason.
It is an incredible triumph of human coordination. But if we connect all this rigid standardization to the bigger picture, it raises a truly profound question about the future of engineering. Everything we have discussed today, the 1400 millimeter guard heights, the voting microprocessors, the light curtains, is based entirely on deterministic logic. We know exactly what the machine will do if the switch is tripped. The code is fixed.
Right, but as machines get smarter, as they begin to incorporate actual artificial intelligence, neural networks, and machine learning into their control architectures, they become non-deterministic. They adapt. They learn to optimize their own movements in ways the original programmer never explicitly wrote.
They become unpredictable.
Precisely. So, as we enter this new era, Will these massive, rigid physical and logic standards have to radically evolve to somehow account for the unpredictable, emergent behavior of AI? Or will the basic, fragile physical limitations of the human body, the length of our arms, the softness of our skin, our vulnerability to heat, always remain the ultimate anchor, dictating exactly how we are forced to build the world around us?
That is a phenomenal question to leave hanging in the air. The human body hasn't changed, but the brains of our machines are evolving at light speed. The standards are going to have to race to keep up with the software.
If you got something useful out of today's episode, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.